In probability theory and statistics, Bayes' theorem, named after Thomas Bayes, describes the probability of an event, based on prior knowledge of conditions that might be related to the event. For example, if the risk of developing health problems is known to increase with age, Bayes' theorem allows the risk to an individual of a known age to be assessed more accurately than simply assuming that the individual is typical of the population as a whole. One of the many applications of Bayes' theorem is Bayesian inference, a particular approach to statistical inference. When applied, the probabilities involved in the theorem may have different probability interpretations. With Bayesian probability interpretation, the theorem expresses how a degree of belief, expressed as a probability, should rationally change to account for the availability of related evidence. Bayesian inference is fundamental to Bayesian statistics, being considered to the theory of probability what Pythagoras' theorem is to geometry. Statement of theorem. Bayes' theorem is stated mathematically as the following equation, where a \displaystyle a and b \displaystyle b are events and p b is not equal to 0 \displaystyle p \nic 0 p a b \displaystyle p is a conditional probability, the probability of event a \displaystyle a occurring given that b \displaystyle b is true. It is also called the posterior probability of a \displaystyle a given b \displaystyle b p b a \displaystyle p is also a conditional probability, the probability of event b \displaystyle b occurring given that a \displaystyle a is true. It can also be interpreted as the likelihood of a \displaystyle a given a fixed b \displaystyle b because p b a equals l a b \displaystyle p equals l p a \displaystyle p and p b \displaystyle p are the probabilities of observing a \displaystyle a and b \displaystyle b respectively without any given conditions. They are known as the prior probability and marginal probability. Proof. For events. For continuous random variables. General case. Examples. Recreational mathematics. Bayes' rule and computing conditional probabilities provide a solution method for a number of popular puzzles, such as the three prisoners problem, the Monty Hall problem, the two-child problem and the two envelopes problem. Drug testing. Suppose a particular test for whether someone has been using cannabis is 90% sensitive, meaning the true positive rate equals 0.90. Therefore, it leads to 90% true positive results for cannabis users. The test is also 80% specific, meaning true negative rate equals 0.80. Therefore, the test correctly identifies 80% of non-use for non-users, but also generates 20% false positives, or false positive rate equals 0.20, for non-users. Assuming 0.05 prevalence, meaning 5% of people use cannabis, what is the probability that a random person who tests positive is really a cannabis user? The positive predictive value of a test is the proportion of persons who are actually positive out of all those testing positive, and can be calculated from a sample as PPV equals true positive / tested positive. If sensitivity, specificity, and prevalence are known, PPV can be calculated using Bayes' theorem. Let P user positive \display P mean the probability that someone is a cannabis user given that they test positive, which is what is meant by PPV. We can write P user positive equals P positive user P user P positive equals P positive user P user P positive user P user plus P positive non-user P non-user equals 0.90 times 0.05 0.90 times 0.05 plus 0.20 times 0.95 equals 0.045 0.045 plus 0.19 19% display style begin aligned p and equals frac ppp and equals frac ppp plus pp and equals frac 0.90 times 0.05 0.90 times 0.05 plus 0.20 times 0.95 equals frac 0.045 0.045 plus 0.19 approximate 19% end aligned. The fact that P positive equals P positive user P user plus P positive non-user P non-user display style P equals PP plus PP is a direct application of the law of total probability. In this case, it says that the probability that someone tests positive is the probability that a user tests positive, times the probability of being a user, plus the probability that a non-user tests positive, times the probability of being a non-user. This is true because the classifications user and non-user form a partition of a set, namely the set of people who take the drug test. This combined with the definition of conditional probability results in the above statement. In other words, even if someone tests positive, the probability that they are a cannabis user is only 19%. This is because in this group, only 5% of people are users, and most positives are false positives coming from the remaining 95%. If 1,000 people were tested, 950 are non-users and 190 of them give false positive. 50 of them are users and 45 of them give true positive. The 1,000 people thus yields 235 positive tests, of which only 45 are genuine drug users, about 19%. See Figure 1 for an illustration using a frequency box, and note how small the pink area of true positives is compared to the blue area of false positives. Sensitivity or specificity. Cancer rate. Even if 100% of patients with pancreatic cancer have a certain symptom, when someone has the same symptom, it does not mean that this person has a 100% chance of getting pancreatic cancer. Assuming the incidence rate of pancreatic cancer is 1/100,000, while 10/99999 healthy individuals have the same symptoms worldwide, the probability of having pancreatic cancer given the symptoms is only 9.1%, and the other 90.9% could be false positives. Based on incidence rate, the following table presents the corresponding numbers per 100,000 people, which can then be used to calculate the probability of having cancer when you have the symptoms. P. Cancer symptoms equals P. Symptoms cancer P. Cancer P. Symptoms equals P. Symptoms cancer P. Cancer P. Symptoms cancer P. Cancer plus P. Symptoms non-cancer P. Non-cancer equals 1 times 0.00001 1 times 0.00001 plus 10/99,999 times 0.99999 equals 1 11 9.1%. Display style begin aligned p and equals frac ppp and equals frac ppp plus pp and equals frac 1 times 0.000011 times 0.00001 plus times 0.99999 equals frac 111 approximate 9.1 end aligned. Defective item rate. A factory produces items using 3 machines A, B, and C which account for 20%, 30%, and 50% of its output respectively. Of the items produced by machine A, 5% are defective. Similarly, 3% of machine B's items and 1% of machine C's are defective. If a randomly selected item is defective, what is the probability it was produced by machine C? Once again, the answer can be reached without using the formula by applying the conditions to a hypothetical number of cases. For example, if the factory produces 1,000 items, 200 will be produced by machine A, 300 by machine B, and 500 by machine C. Machine A will produce 5% times 200 equals 10 defective items, machine B 3% times 300 equals 9, and machine C 1% times 500 equals 5, for a total of 24. Thus, the likelihood that a randomly selected defective item was produced by machine C is 5/24. This problem can also be solved using Bayes' theorem. Let Xi denote the event that a randomly chosen item was made by the ith machine. Let Y denote the event that a randomly chosen item is defective. Then, we are given the following information. P X A equals 0.2. P X B equals 0.3. P X C equals 0.5. Display style P equals 0.2 quad P equals 0.3 quad P equals 0.5. If the item was made by the first machine, then the probability that it is defective is 0.05, that is, P equals 0.05. Overall, we have P Y X A equals 0.05. P Y X B equals 0.03 p y x c equals 0.01 backslash display style p equals 0.05 backslash quad p equals 0.03 backslash quad p equals 0.01. To answer the original question, we first find p. That can be done in the following way. P y equals I p y x I p x I equals 0.05 0.2 plus 0.03 0.3 plus 0.01 0.5 equals 0.024 backslash display style p equals backslash sum underscore ipp equals plus plus equals 0.024. Hence, 2.4% of the total output is defective. We are given that y has occurred, and we want to calculate the conditional probability of xc. By Bayes' theorem, p x c y equals p y x c p x c p y equals 0.01 0.50 0.024 equals 5.24 backslash display style p equals backslash frac pp equals backslash frac 0.01 backslash dot 0.50 0.024 equals backslash frac 524. Given that the item is defective, the probability that it was made by machine C is 5/24. Although machine C produces half of the total output, it produces a much smaller fraction of the defective items. Hence the knowledge that the item selected was defective enables us to replace the prior probability p equals 1/2 by the smaller posterior probability p equals 5/24. Interpretations. The interpretation of Bayes' rule depends on the interpretation of probability ascribed to the terms. The two main interpretations are described below. Figure 2 shows a geometric visualization. Bayesian interpretation. In the Bayesian interpretation, probability measures a degree of belief. Bayes' theorem links the degree of belief in a proposition before and after accounting for evidence. For example, suppose it is believed with 50% certainty that a coin is twice as likely to land heads than tails. If the coin is flipped a number of times and the outcomes observed, that degree of belief will probably rise or fall, but might even remain the same, depending on the results. For proposition A and evidence B, P, the prior, is the initial degree of belief in A. P, the posterior, is the degree of belief after incorporating news that B is true. The quotient P/P represents the support B provides for A. For more on the application of Bayes' theorem under the Bayesian interpretation of probability, see Bayesian inference. Frequentist interpretation. In the frequentist interpretation, probability measures a proportion of outcomes. For example, suppose an experiment is performed many times. P is the proportion of outcomes with property A and P is the proportion with property B. P is the proportion of outcomes with property B out of outcomes with property A, and P is the proportion of those with A out of those with B. The role of Bayes' theorem is best visualized with tree diagrams such as Figure 3. The two diagrams partition the same outcomes by A and B in opposite orders, to obtain the inverse probabilities. Bayes' theorem links the different partitionings. Example: forms, events, simple form, alternative form. Extended form. Random variables. Consider a sample space omega generated by two random variables x and y. In principle, Bayes' theorem applies to the events A equals x and B equals y. P x equals x, y equals y equals P y equals y, x equals x, P x equals x, P y equals y. Display style p equals frac p. However, terms become zero at points where either variable has finite probability density. To remain useful, Bayes' theorem must be formulated in terms of the relevant densities. Simple form. Extended form. Bayes' rule in odds form. Bayes' theorem in odds form is O A 1 A 2 B equals O A 1 A 2 lambda A 1 A 2 B display style O equals O lambda, where lambda A 1 A 2 B equals P B A 1 P B A 2 display style lambda equals frac pp is called the Bayes factor or likelihood ratio. The odds between two events is simply the ratio of the probabilities of the two events. Thus, O A 1 A 2 equals P A 1 P A 2 display style O equals frac pp comma O A 1 A 2 B equals P A 1 B P A 2 B display style O equals frac pp comma. Thus, the rule says that the posterior odds are the prior odds times the Bayes factor, or in other words, the posterior is proportional to the prior times the likelihood. In the special case that A 1 equals A display style A underscore 1 equals A and A 2 equals A display style A underscore 2 equals nega. One writes O A equals O A equals P A slash 1 P A display style O equals P slash, and uses a similar abbreviation for the Bayes factor and for the conditional odds. The odds on A display style A is by definition the odds for and against A display style A. Bayes' rule can then be written in the abbreviated form O A B equals O A lambda A B display style O equals O lambda. Or, in words, the posterior odds on A display style A equals the prior odds on A display style A. times the likelihood ratio for A backslash display style A given information B backslash display style B. In short, posterior odds equals prior odds times likelihood ratio. For example, if a medical test has a sensitivity of 90% and a specificity of 91%, then the positive Bayes factor is lambda plus equals P true positive slash P false positive equals 90% slash 100% 91% equals 10 backslash display style backslash lambda underscore plus equals P slash P equals 90 backslash percent slash equals 10. Now, if the prevalence of this disease is 9.09%, and if we take that as the prior probability, then the prior odds is about 110. So after receiving a positive test result, the posterior odds of actually having the disease becomes 1:1. In other words, the posterior probability of actually having the disease is 50%. If a second test is performed in serial testing, and that also turns out to be positive, then the posterior odds of actually having the disease becomes 10:1, which means a posterior probability of about 90.91%. The negative Bayes factor can be calculated to be 91% slash equals 9.1, so if the second test turns out to be negative, then the posterior odds of actually having the disease is 1:9.1, which means a posterior probability of about 9.9%. The example above can also be understood with more solid numbers. Assume the patient taking the test is from a group of 1,000 people, where 91 of them actually have the disease. If all these 1,000 people take the medical test, 82 of those with the disease will get a true positive result, 9 of those with the disease will get a false negative result, 827 of those without the disease will get a true negative result, and 82 of those without the disease will get a false positive result. Before taking any test, the patient's odds for having the disease is 91:909. After receiving a positive result, the patient's odds for having the disease is 91,909 times 90.1% 9.0% equals 91 times 90.1% 909 times 9.0% equals 1 backslash display style backslash frac 91,909 backslash times backslash frac 90.1 backslash percent 9.0 backslash percent equals backslash frac 91 backslash times 90.1 backslash percent 909 backslash times 9.0 backslash percent equals 1:1, which is consistent with the fact that there are 82 true positives and 82 false positives in the group of 1,000 people. Correspondence to other mathematical frameworks. Propositional logic. Using P B A equals 1 P B A backslash display style P equals 1 P. Twice, one may use Bayes' theorem to also express P B A backslash display style P in terms of P A B backslash display style P, and without negations P B A equals 1 P A B P B P A backslash display style p equals 1 backslash left backslash right, backslash frac pp. When p a equals 1, p a is not equal to 0. Backslash display style p equals 1 p backslash nic 0. From this we can read off the inference. P a b equals 1 p b a equals 1. Backslash display style p equals 1 backslash implies p equals 1. In words, if certainly b backslash display style b implies a backslash display style a, we infer that certainly a backslash display style backslash nega implies b backslash display style backslash negb, where p b is not equal to 0. Backslash display style p backslash nic 0. The two implications being certain are equivalent statements. In the probability formulas, the conditional probability p a b backslash display style p generalizes the logical implication b a backslash display style b backslash implies a. We're now beyond assigning true or false, we assign probability values to statements. The assertion of b a backslash display style b backslash implies a is captured by certainty of the conditional. The assertion of p a b equals 1 backslash display style p equals 1. Relating the directions of implication, Bayes' theorem represents a generalization of the contraposition law, which in classical propositional logic can be expressed as b a b backslash display style backslash iff. Note that in this relation between implications, the positions of a backslash display style a resp b backslash display style b get flipped. The corresponding formula in terms of probability calculus is Bayes' theorem, which in its expanded form involving the prior probability / base rate a backslash display style a of only a backslash display style a is expressed as p a b equals p b a p b a plus p b a backslash display style p equals p backslash frac a p backslash a plus p backslash a. Subjective logic. Bayes' theorem represents a special case of deriving inverted conditional opinions in subjective logic expressed as omega a b s omega a b s equals omega b a s omega b a s a backslash display style equals backslash wide tilde backslash phi a underscore a comma, where backslash display style backslash wide tilde backslash phi denotes the operator for inverting conditional opinions. The argument omega b a s omega b a s backslash display style denotes a pair of binomial conditional opinions given by source S / display style S and the argument A / display style A_A denotes the prior probability of A / display style A. The pair of derivative inverted conditional opinions is denoted omega A B S omega A B S / display style. The conditional opinion omega A B S / display style /omega _ A / mid BS generalizes the probabilistic conditional P A B / display style P, i.e. in addition to assigning a probability the source S / display style S can assign any subjective opinion to the conditional statement A B / display style. A binomial subjective opinion omega A S / display style /omega _ AS is the belief in the truth of statement A / display style A with degrees of epistemic uncertainty, as expressed by source S / display style S. Every subjective opinion has a corresponding projected probability P omega A S / display style P. The application of Bayes' theorem to projected probabilities of opinions is a homomorphism, meaning that Bayes' theorem can be expressed in terms of projected probabilities of opinions P omega A B S equals P omega B A S A P omega B A S A plus P omega B A S A / display style P equals / frac pa plus pa dot. Hence, the subjective Bayes theorem represents a generalization of Bayes' theorem. Generalizations. Conditioned version. A conditioned version of the Bayes theorem results from the addition of a third event C / display style C on which all probabilities are conditioned P A B C equals P B A C P A C P B C / display style P equals / frac P / PP. Derivation. Bayes' rule with three events. In the case of three events, A, B, and C, it can be shown that History. Bayes' theorem is named after the Reverend Thomas Bayes, who first used conditional probability to provide an algorithm that uses evidence to calculate limits on an unknown parameter, published as an essay towards solving a problem in the doctrine of chances. He studied how to compute a distribution for the probability parameter of a binomial distribution. On Bayes' death, his family transferred his papers to his old friend, Richard Price, who over a period of 2 years significantly edited the unpublished manuscript, before sending it to a friend who read it aloud at the Royal Society on December 23, 1763. Price edited Bayes' major work, an essay towards solving a problem in the doctrine of chances, which appeared in Philosophical Transactions, and contains Bayes' theorem. Price wrote an introduction to the paper which provides some of the philosophical basis of Bayesian statistics and chose one of the two solutions offered by Bayes. In 1765, Price was elected a Fellow of the Royal Society in recognition of his work on the legacy of Bayes. On April 27 a letter sent to his friend Benjamin Franklin was read out at the Royal Society, and later published, where Price applies this work to population and computing life annuities. Independently of Bayes, Pierre-Simon Laplace in 1774, and later in his 1812 Théorie analytique des probabilités, used conditional probability to formulate the relation of an updated posterior probability from a prior probability, given evidence. He reproduced and extended Bayes' results in 1774, apparently unaware of Bayes' work. The Bayesian interpretation of probability was developed mainly by Laplace. Sir Harold Jeffreys put Bayes' algorithm and Laplace's formulation on an axiomatic basis, writing that Bayes' theorem is to the theory of probability what the Pythagorean theorem is to geometry. Stephen Stigler used a Bayesian argument to conclude that Bayes' theorem was discovered by Nicholas Saunderson, a blind English mathematician, some time before Bayes. That interpretation, however, has been disputed. Martin Hooper and Sharon McGrain have argued that Richard Price's contribution was substantial. By modern standards, we should refer to the Bayes-Price rule. Price discovered Bayes' work, recognized its importance, corrected it, contributed to the article, and found a use for it. The modern convention of employing Bayes' name alone is unfair but so entrenched that anything else makes little sense. Use in genetics. In genetics, Bayes' theorem can be used to calculate the probability of an individual having a specific genotype. Many people seek to approximate their chances of being affected by a genetic disease or their likelihood of being a carrier for a recessive gene of interest. A Bayesian analysis can be done based on family history or genetic testing, in order to predict whether an individual will develop a disease or pass one on to their children. Genetic testing and prediction is a common practice among couples who plan to have children but are concerned that they may both be carriers for a disease, especially within communities with low genetic variance. The first step in Bayesian analysis for genetics is to propose mutually exclusive hypotheses. For a specific allele, an individual either is or is not a carrier. Next, 4 probabilities are calculated: prior probability, conditional probability, joint probability, and posterior probability. This type of analysis can be done based purely on family history of a condition or in concert with genetic testing. Using pedigree to calculate probabilities. Example of a Bayesian analysis table for a female individual's risk for a disease based on the knowledge that the disease is present in her siblings but not in her parents or any of her 4 children. Based solely on the status of the subject's siblings and parents, she is equally likely to be a carrier as to be a non-carrier. However, the probability that the subject's 4 sons would all be unaffected is 1/16 if she is a carrier, about 1 if she is a non-carrier. The joint probability reconciles these 2 predictions by multiplying them together. The last line is calculated by dividing the joint probability for each hypothesis by the sum of both joint probabilities. Using genetic test results. Parental genetic testing can detect around 90% of known disease alleles in parents that can lead to carrier or affected status in their child. Cystic fibrosis is a heritable disease caused by an autosomal recessive mutation on the CFTR gene, located on the Q arm of chromosome 7. Bayesian analysis of a female patient with a family history of cystic fibrosis, who has tested negative for CF, demonstrating how this method was used to determine her risk of having a child born with CF. Because the patient is unaffected, she is either homozygous for the wild-type allele, or heterozygous. To establish prior probabilities, a Punnett square is used, based on the knowledge that neither parent was affected by the disease but both could have been carriers. Given that the patient is unaffected, there are only 3 possibilities. Within these 3, there are 2 scenarios in which the patient carries the mutant allele. Thus the prior probabilities are 2-3 and 1-3. Next, the patient undergoes genetic testing and tests negative for cystic fibrosis. This test has a 90% detection rate, so the conditional probabilities of a negative test are 1/10 and 1. Finally, the joint and posterior probabilities are calculated as before. After carrying out the same analysis on the patient's male partner, the chances of their child being affected is equal to the product of the parents' respective posterior probabilities for being carriers times the chances that 2 carriers will produce an affected offspring. Genetic testing done in parallel with other risk factor identification. Bayesian analysis can be done using phenotypic information associated with a genetic condition, and when combined with genetic testing this analysis becomes much more complicated. Cystic fibrosis, for example, can be identified in a fetus through an ultrasound looking for an echogenic bowel, meaning one that appears brighter than normal on a SCAN2. This is not a foolproof test, as an echogenic bowel can be present in a perfectly healthy fetus. Parental genetic testing is very influential in this case, where a phenotypic facet can be overly influential in probability calculation. In the case of a fetus with an echogenic bowel, with the mother who has been tested and is known to be a CF carrier, the posterior probability that the fetus actually has the disease is very high. However, once the father has tested negative for CF, the posterior probability drops significantly. Risk factor calculation is a powerful tool in genetic counseling and reproductive planning, but it cannot be treated as the only important factor to consider. As above, incomplete testing can yield falsely high probability of carrier status, and testing can be financially inaccessible or unfeasible when a parent is not present. See also Bayesian epistemology, inductive probability, quantum Bayesianism. Why most published research findings are false, a 2005 essay in Metascience by John Ioannidis. Notes.